You can stop time just by looking. That sentence sounds absurd at first. Everyone learns that time flows constantly, that observation is passive, that looking at something doesn't change how it behaves. Physics teaches us that measurement reveals reality, but doesn't create it. The common understanding is that your eyes record what happens, but cannot influence what happens. But here's a secret that quantum mechanics has been whispering since the 1970s. If you watch a quantum system carefully enough, you can freeze its evolution completely. The act of observation doesn't just reveal quantum processes, it controls them, slows them, and can stop them entirely. This isn't philosophy. It isn't metaphor. This is one of the strangest demonstrations that consciousness and physical reality are connected in ways that classical physics never imagined. But first, try a small experiment with yourself. Set a timer for 60 seconds and stare at the second hand of a clock or watch. Focus intently on each tick, each movement, each transition from one second to the next. Now pay attention. What happened to your perception of time? Some of you felt time crawling by. Each second seemed to stretch endlessly as you focused on the clock's movement. Your attention made time feel slower, more deliberate, almost frozen compared to normal experience. But others, and here's the interesting part, felt something different. Perhaps time seemed to speed up under intense observation. Maybe the focused attention created a meditative state where 60 seconds passed in what felt like moments. But neither group experienced what quantum mechanics says actually happens during observation. Feynman often used examples like this to illustrate the gap between human intuition and physical reality. This tells us something fundamental. What you experience as the relationship between observation and time is not what quantum systems actually experience under measurement. The difference isn't psychological, it's physical. So when we talk about quantum measurement, you need to abandon your intuitions about passive observation. We need to stop talking about how measurement feels and start talking about what it actually does. In Feynman's approach, physics had to address measurable phenomena without assuming human experience translated to quantum reality. This means don't ask what does it feel like to watch something. That's a question about psychology. Instead ask how does observation affect quantum evolution? What happens when we measure frequently? And the answer is almost magically counterintuitive. Frequent observation can completely halt quantum processes. Think of a pot of water coming to a boil. Left alone, the water heats up, bubbles form, and boiling begins after a predictable time. You can measure the temperature, time the process, predict when boiling starts. Quantum systems are something like that pot, except quantum mechanics says that if you check the temperature frequently enough, the water will never reach boiling point, not because measurement cools it down, but because the act of checking prevents the heating process from proceeding. Here's the strangest part. This prevention happens even when measurement requires no energy and causes no physical disturbance. To understand this, let's do a quantum thought experiment. Right now, imagine you have an unstable atomic nucleus that should decay within 1 hour. Quantum mechanics gives precise probabilities for when decay will occur, but cannot predict the exact moment. But here's what quantum mechanics also predicts. If you check whether the nucleus has decayed every few seconds, the decay process slows down dramatically. If you check every millisecond, decay becomes extremely unlikely. If you could check continuously, the nucleus would never decay at all. As explained in quantum measurement theory, this effect occurs because each measurement resets the quantum system to its initial state. The nucleus forgets how long it has been unstable and must restart the decay process from the beginning. Think of it like quantum amnesia. Frequent observation erases the system's memory of its own evolution, forcing it to restart each process over and over without making progress toward completion. Now replace nucleus with any quantum process and decay with evolution. Every quantum system in the universe, atoms, molecules, particles, can have its natural evolution halted by sufficiently frequent observation. The universe contains processes that stop progressing when watched carefully enough. You don't notice this in everyday life, of course. Classical objects involve so many quantum particles that the effect averages out. But for individual quantum systems, observation literally controls the passage of time. Let's examine the physics. Quantum evolution occurs through wave function development over time. Left alone, quantum systems explore all possible states simultaneously through superposition, gradually evolving toward measurement outcomes. But each observation collapses the wave function back to a definite state, erasing the accumulated evolution and forcing the system to restart its quantum development from a known condition. When observations occur faster than natural evolution timescales, the quantum system never accumulates enough development time to reach new states. It becomes frozen in its initial condition through repeated measurement-induced resets. This isn't theoretical speculation. Experiments with trapped ions, atomic systems, and quantum dots have demonstrated quantum Zeno effect repeatedly. Frequent measurement can slow quantum tunneling, prevent atomic decay, and halt chemical reactions. As Feynman understood from his work on quantum mechanics, this reveals something profound about the relationship between information and physical evolution. Knowledge acquisition through measurement doesn't just reveal reality, it participates in creating reality by determining which quantum possibilities become actual. Here's the mind-bending part. The quantum Zeno effect suggests that observation has temporal power over physical processes. Your decision to measure frequently can literally control how fast quantum evolution proceeds through measurement-induced time dilation. This measured time isn't just clock time or subjective time, it's physical evolution time, the rate at which quantum systems explore new possibilities and develop toward different states. From the quantum system's perspective, frequent observation stretches the time available for evolution, making each development phase take longer to complete. But wait, there's also the opposite effect called quantum anti-Zeno effect. Under certain conditions, frequent measurement can accelerate quantum evolution rather than slowing it down. Which effect occurs depends on the relationship between measurement frequency and the natural timescales of quantum evolution. Sometimes observation acts like temporal brakes, sometimes like temporal acceleration. This means observation doesn't just passively reveal quantum reality, it actively controls the temporal relationship between quantum systems and their environment through measurement-controlled time manipulation. As Feynman explored in his development of quantum electrodynamics, this temporal control through measurement reveals that information and time are more intimately connected than classical physics suggested. Now let's pause here and think operationally. Is observation a passive recording, or is it active participation? In quantum mechanics, observation involves interaction between measuring apparatus and quantum systems, but the quantum Zeno effect shows that this interaction can control temporal evolution even when the measurement extracts no energy and causes no classical disturbance. A more accurate description. Observation is information acquisition that participates in determining the temporal development of physical processes through measurement-induced state resets. Think of it this way. Saying measurement reveals what was already there is like saying the thermometer measures temperature without affecting it. But quantum thermometers don't just read quantum temperature, they participate in determining how quickly quantum temperature changes. The quantum Zeno effect shows us that information extraction has temporal consequences that extend beyond simply revealing pre-existing properties. Consciousness isn't just observing physical reality. Through measurement choices, consciousness participates in controlling the temporal evolution of quantum processes. But we're not done yet, because this has far more profound implications for the nature of time, consciousness, and reality. If conscious observation can control quantum evolution rates, what does this tell us about the relationship between mind and physical time? As Feynman explored in his work on quantum mechanics and measurement, quantum systems exist in superposition until observation collapses possibilities into definite outcomes. The quantum Zeno effect extends this by showing that observation frequency controls the rate of this collapse process. Think of consciousness as temporal conductor. You're not just witnessing physical processes, you're helping to determine the rhythm at which quantum reality develops through your measurement decisions. The quantum Zeno effect might be telling us that time itself, at the quantum level, operates according to principles that consciousness can influence through information-gathering choices. Who controls quantum time, the universe or the observer? Both, through the interaction we call measurement. This is the part that should expand every assumption about passive observation. Conscious attention isn't separate from physical processes. It participates in determining temporal relationships between quantum systems and their development possibilities. So what's the meaning of this knowledge? You can't directly experience quantum Zeno effect in everyday life. Classical objects involve too many quantum particles for individual temporal control, but understanding this effect reveals something profound about consciousness and physical time. The quantum Zeno effect isn't just about stopping quantum evolution, it's about the deep connection between knowledge-seeking consciousness and the temporal development of physical reality through measurement interaction. Let's return to where we started. You can stop time just by looking. Does that make sense now? Stopping time requires quantum systems and frequent measurement. Looking provides information acquisition that resets quantum evolution and prevents temporal development toward new states. You are the one whose attention can influence quantum development rates. You are the one whose observation choices help determine how quickly quantum reality evolves through measurement-controlled temporal manipulation. Time develops through the collaborative relationship between conscious observers and quantum systems. When you understand quantum Zeno effect, you're recognizing a connection between consciousness and physical time that classical physics never imagined. Look at quantum systems frequently enough. Time slows down because you decided to watch.